secret way only to turn it once there. Sorry.
Okay.
So, good evening everybody, and we're having here today Craig Box at Google. Oh.
On again.
No, but those are different lights. Seriously.
Really?
Yeah.
Every second light.
I think
Good,
so.
yeah, no.
Oh.
No,
No.
I just click once. I'm not touching it.
Really?
Okay, we're playing the light game.
Yeah. Continue.
So-
Ignore the lights.
Welcome to Cloud GDG Group, and we'll be having here today Craig Box at Google, and here we'll be talking actually about the cluster and container management in Kubernetes, and we'll give you the stage to start your thing.
Cool. Thank you everyone for coming along. Can everyone hear me, or would you like me to use the mic? I don't need to. I'm pretty loud, so.
If you decide you need.
Yeah. Tel's also pretty loud, so between us. Okay. So I'm going to talk a little bit about Painless container management and how we enable that with Kubernetes. How we've got to where we are from the system we built inside Google over the last couple of years. So first of all, I'd like to kick off a little bit with history. So my role at Google is looking after helping our sales teams understand the compute ecosystem, especially around containers. And there's an interest in this. I like to tell the story of how we got
Sorry.
how we got from where we were. So, turn back the clock to say around 2002, around 15 years ago. We were operating very similar way than a lot of other enterprises with data centers. So you had every application you wanted to run, you needed to raise a ticket, and then a machine would be given to you to run your application. It's very hard to run and manage this at scale. We wanted to figure out how we could do more with fewer people and move away from that model and get into a multi-tenant environment. Because you start having things running on the same computer, you find that if this workload is really loud, uses a lot of the CPU, a lot of the memory on the machines, then you don't want to be sitting next to it. So people very much wanted to keep this isolation. And the bigger the fleet got, the more machines we had, the worse that it was. We'd have a situation that an intern would come along and that would map reduce and test something out, which would be really easy, but then that would mean you could potentially take search index offline for people wanting to do searches. So we had early isolation tools like chroot and nice, and it limits your ability if those are the only tools that you have. So we really started looking at ways of how we could solve this isolation problem. Then a few years later, we developed a thing called C groups, which was originally called process containers. And this technology was a way to build these isolation boundaries, so you could say to a particular process or group of processes, you only have access to a certain amount of memory or certain CPU, and you could guarantee that that would be what you'd land up being allowed. So that you knew that if your work was running on the same machine as somebody else's, it was okay. You weren't going to trample on them. And then, because we have this safe isolation, we're now able to put more work. We don't have to say, this work might one day spike up and use all the rest of the stuff, so we can't use this spare space. We can start filling that space in, which means we can do more with fewer computers than we did previously. And it's not because the people who operate it are doing anything different, but it's because we're making it a machine decision as to how we pack things, rather than people saying this app needs to run on this machine and pack that down. So we've evolved our system over time, we've made a lot of mistakes along the way, and we've learned a lot of very important lessons that we wanted to carry forward. Bringing on a few years again, we've seen this utilization that we have as a really great competitive advantage. We can do more than other competitors do. You can't come along and beat us at our own game. We started talking about this, but only really sort of conceptually, so that we go to academics, we'd publish papers and things, but we started talking about the second thing that we built, and it was a really big secret that we were talking about, Borg with our first internal system. So we published this paper on Omega, which was our second system. And then, around the same time, Docker was released. Docker is a container image format and build tools and a really nice way of sort of marketing and making easy to use this idea of containers and packaging things in this way. And it really started an explosion of interest in this space. So all of a sudden we thought, wow, people are talking about this, we should share more what we're doing and we should help get involved. And we had a very awkward conversation. We said, well, we've got this secret thing. And someone actually went to the boss and said, well, can we give that away? What would happen if we made a version of this? And our experience building stuff to that point had showed that we aren't using the same tools inside Google as people outside are using. So we needed to not just give away the thing that we had, but we needed to build something that worked with Docker and worked with everything else in the industry. And the time was right to share our experiences and then also learn from other people who are doing the same kind of thing. And so that culminated in Kubernetes in June 2014. Kubernetes, for those of you who haven't come across it yet, it's a Greek word. It means the captain of a ship. And it means it's root of some other English words like governor. And it's a good way to think about it. It governs a system of containers. It is inspired by what we do internally, but it's a complete new implementation written in Go, which is a great systems programming language. It supports running on cloud, it supports running on bare metal, it runs on x86, on ARM, you can run it on your Raspberry Pi on your desk. You can support not only the Docker runtime, but now we have support for CoreOS's Rocket and the Hyper runtime. And on top of everything, it's 100% open source. We have a hosted version of it, which we call Google Container Engine. Just one click and get yourself a nice easy cluster. What this is a distributed systems toolkit. We want to make it as easy to make reliable, scalable systems as it is to write Hello World on your first day of computer science. And all of those lessons that we learnt, everything we've built in our own system, we want you to have that and say, we're starting from here now, rather than having to re-implement everything. You can build on top of that. All of that work is yours for free. So some of the principles that we came up with here. The whole world isn't like Google. We take everything from source and we build absolutely everything from one single giant open code repository. But other people take code off the shelf. They take MySQL, Nginx, and they put that in containers and run them. And even if people are going to rewrite applications, they're not going to do it all at once and they're not going to do it quickly. So we want to make it easy to run what you have, to run independent parts, so you can use these parts connected to your new code and your old code. To be able to make it easy to interchange and replace the components so you can run on different vendors or run connecting to different systems. And we're starting to see open hardware, we're starting to see this real shift, especially with what Microsoft have done recently, open by default. So we wanted this to be an open standard which people would be encouraged to run anywhere. We wanted to take these experiences and make it possible for you to focus on running applications and not running the infrastructure underneath. So we said we want you to learn from our mistakes, and one of the biggest mistakes is when we say things are too tightly coupled. So in previous times you'd find if you make a change in one place and it breaks something somewhere else. So people fear deploying an application or making a change because they think it's not going to work everywhere. And so you have this fear of changing or breaking software, and so you can't move forward. All of the things that you need to be agile go away if you couple your software together too hard. And when you think about how we put software on machines previously, we couple it like this. We have our physical infrastructure, we have some services we want to run, we'll just put it on a machine. So we might end up saying that the first machine has some back-end instance on it and maybe a couple of front-end pods, so on. But then let's say I want to upgrade something on this machine. Well, it might break one of those things. It might be that the green thing needs something newer, but the yellow things will break because it introduces a different version of the library. So that is that tight coupling that I talked about. And how we work with Kubernetes is we think of a logical infrastructure. So you look at your applications like this. You say, I want to work on the front ends. The container format lets you package together the application code and the libraries so that wherever they land, you're running with the code correctly coupled. And then you don't worry about what the machines are. You say a different group of people can specialize in providing machines. But you have this platform upon which you can put your own applications with none of those unintended consequences. So I'll just introduce the core concepts of Kubernetes. A pod is a small group of containers that are tightly coupled together. So you want the smallest coupling that makes sense, and you think about that if you have a program, a web server serving out content, it actually has to have that content. And you don't want to have to rebuild the web server every time you change the content. So you might have a pod which has the container with the web server and maybe some code that goes and pulls the latest version of the content. Or something that sends logs off to a log server or something. These things always go together. They always should end up scheduled on the same machine. In our world, we keep them on the same IP address, so it's very easy to communicate between them. You don't need to do any service discovery or anything like that. Now we need to move on to flying the plane in our example rather than programming, sorry, we don't want to have to think about it like flying a plane. You want to program an autopilot and say, work this way. So we have a loop that says, I've said I want to have 10 replicas. The system only has 7. Perhaps you have a scale, you have a node that failed. It will say, I want them to be 10, and it will find a place to run 3 more. And then you've got 10, it says I'm fine. And then that just keeps running in a loop, going around and around to check that the system has the state that you want. Later on you might say, I only want them to be 4 replicas now, and so it will go through and kill some off. So it's continually making sure that what you have asked for declaratively is what you get. Now if you think of any application you've run before, the hardest thing is moving from one of something to more than one. All of a sudden you have to start thinking about how these things relate to each other. Kubernetes abstracts this with a concept called a service, which is a set of running pods that work together. So you might use it behind a load balancer, for example. And now instead of having to connect to a service discovery system and then say, where are these things, and then figure out yourself how you talk to it, services give you an IP address endpoint that you just connect to, and it will automatically load balance you to one of the pods, one of the replicas of that service that's running in your cluster. Now when you're dealing with a system that can change dynamically like this, because that's how you've got it programmed, you need a way of being able to group things together. Again, this is another one of the lessons from our internal system, is we didn't have this, so we'd end up with container names would be things like Gmail-Asia Pacific version 4 without this bug or something. You'd have these giant long names for what a container was. So we've moved to this key value metadata thing where you can tag each pod with anything you want. So it has a name, but it also might have a phase. It might say this is a production, this is back end, this is front end, and so on. And then you can address your service. You could say, this service represents all of the pods that are in phase production and of type front end. And so that way, when you hit that IP address, it continually looks in your cluster through one of these control loops, finds all of the things that match that, and makes sure that the service will always redirect you to these things. So you don't have to worry about calling out to anything. Now these components come together to give you a few things. We talked, obviously, you can do more with your computers. You can do more for less money. So lower utilization is definitely easier to manage, but we want to make it as easy to manage at high utilization. Most people running virtual machines get about 5% usage because of the overheads that they have. We like to think that the average in Kubernetes is at least 20%, and you can go a lot further than that if you're willing to pack things down. So think of it like quadrupling your data center for free. We have a customer quote here for someone who said they managed to cut the number of machines that they use in half just by using Kubernetes and Container Engine. So once you've got this automated system you can trust, it's very easy to do testing. You can copy a file down, see if it runs. If it doesn't work, you just connect your service back to the old version rather than the new one. You can use this for continuous integration. You can use it for continuous deployment. You don't have to understand anything other than what your containers are. Because these containers are self-packaged, they're the same in development and testing. So your new environments become the same and you reduce your risk. So that makes it easy to fail fast, which means you can try new ideas, see what works. Kubernetes also enables specialization within teams. So if you come from an infrastructure background, people come to you and say, hey, I need you to upgrade this library. And you say, well, I'm not sure what will happen. And if you're an application developer, you might need to go and say, hey, I need you to upgrade this library. And your infrastructure guy says, oh, I'm not sure what will happen. And wouldn't it be great if these people just didn't need to talk to each other? If the contract was there and he said, well, I'm going to run this thing and the system will work, and these people know that the applications provided just run, and let you build out disciplines like cluster operations. So below that line we had before, you can have people who look after the cluster, tune it to run, and they don't need to care what the applications that run on it are. And further, the people above the line who are writing the applications, they don't need to know if it's a cloud underneath, or if it's bare metal, or what it happens to be. The system abstracts that stuff away, so that if you need to get resources, it will call whatever the right thing is for the environment that you're running. And that enables us to do our internal disciplines of site reliability engineering, where we have programmers manage these fleets as if they're an application rather than operating these machines. You can take your workload, run it on wheels, you can start on-premise and move to cloud, you can start on a cloud, move to another cloud, you can run in any environment you want. If you run on Google and it turns out that we're not the best, we'll be very sad and very surprised, but it is possible to take your workload and run it somewhere else, and that's very important to us. So after 15 years of planning and about 5 major releases in the last 18 months, we've got the basic components down really good. And we're starting to talk now about the future and what we want to build on top of the single environment. And I'll talk through a few points and then we'll do a little demo. So the most recent release, we've made it a lot easier to turn these clusters on. You just have to have a few virtual machines or servers, and then previously you had to do quite a complicated dance to get them all connected. And this is a hard problem to solve, to have these distributed state machines, but we want to make it very easy. It's one click on Container Engine, but with the new work in Kubernetes 1.4, it's now possible to start a cluster with 2 commands, which I think I've written there, on your own environment. So basically you go to one machine, say initialize the master, it gives you a token, you go to a second machine, you say join that master with that token, like that, and then you have your cluster created. And then you're running a couple of minutes later. When you go running, we know that there are a lot of people who want to operate in a GUI environment. They find it a lot easier to manage their environment, so our dashboard continues to improve.
And the Minikube has the same behavior and the same GUI?
See if I can fix that color there for you. Yes, so I haven't got anything here about Minikube, but I should say that it is possible to run this on your laptop. There's a tool called Minikube, which is just a little download a VM, automatically build an environment that you're running a laptop that has a little Kubernetes cluster. It's again 2 commands to get started. It's a really easy way. I'll show you again. So I can either talk a bit more and do a demo at the end, or I can show you what it looks like now and then talk a bit more.
Whatever you choose.
Well, that's just like the lights all over again, isn't it? Alright, we'll go through the slides, we'll go quickly through it, and then we'll do that one part. So, a single cluster of machines in a place, at Google we define a cluster as machines that are connected on a high-speed network, which means they're probably in the same place as each other. But you want to run not only in this location, but maybe in another country, or maybe on a different provider. And it doesn't make sense to have a single cluster that spans all of those things, because 2 machines here are very close to each other, but one here and one far away, they have a lot of lag. So you can't guarantee that the replication, for example, will work the way you might expect it to. I actually have some notes on that. So co-located machines. Separate failure domains is important. So everything within a single cluster, a failure here won't affect machines somewhere else. Here's how you interact with the cluster. So as a human operator or a service account, you send some API commands, or you run the dashboard I showed you before, connecting to the master in your cluster, and then that sends out to the nodes. So these nodes here, these might be virtual machines, so you may have 3 nodes here. They each run a thing called a kubelet, which is the little agent that runs to be asked what the state of the machine is to help feedback into those controllers. And then also it accepts instruction that says, I want to start some work, and then distribute that out to the machines. It looks basically like that. So it is possible today to manage multiple regions, but you have to do everything manually. But ultimately, what we want to do is move. What are we going to do in the case we want to load balance between those things? We want to move to this. And what we have here is you issue, again, commands, API calls to a control plane, and then instead of thinking about just nodes at the back end, we actually treat these as completely separate clusters. And this is a thing called federation. Federations, we've been working on the last couple of releases, and we're evolving it very quickly. So what you'll do here is you'll create some clusters, 4 clusters in this example. These ones here are all running on Google. Then you deploy the control plane, and then we pick one of the clusters here to act as the federation master. And on that machine, you end up with the same components that you get in a single cluster. So we have an API server, and what that means is that you're using the same commands and the same API as if you were addressing a single cluster to access multiple things that are running in multiple regions. So you might issue a command, then to join them all to the cluster. This is an example of one of the configuration files, the YAML file for Kubernetes. Here we have a thing called a replica set, where we say that of a particular thing, we have a container, Nginx version 1.1. We want to have 4 replicas of this somewhere within our cluster or in our federation. So if we send that command to one cluster, it might send it out to multiple nodes, or it might find a way to pack them in together. In this case, what we'd do is we'd send it to the federation, and now we have this one thing running across 4 different places. This might be useful if you want to run a worldwide geographically replicated application, or if you want to run something that runs on multiple cloud providers so that you know that you're safe in the instance that anyone's offline.
You still have a single point, like if I'm accessing it from Japan, the federation master is in the US, wouldn't it make more sense to access it through a federation master that is in Japan?
Yeah, the master and the nodes or the clusters that run it. So you only need this part when you're telling it to change something. So if you're sending a command that says, change my workload, deploy something, then that goes out to the nodes or to the clusters. From that point on, we'll see in a second like a load balancer pointing to these clusters. It's only the instruction piece. So it's not so, the same thing, like you can make this replicated if you want. You can make it multi-zone, highly available. But if you do that, then if this is offline for 2 minutes, then you can't change anything, but all the work keeps running. So you don't need to worry about that.
You can have multi-master, it's just the etcd cluster.
Yes.
Have the old state.
Yep. Yeah, so the other thing, if we went back a bit, they had the API server before, we've also got this thing called etcd, which is the database that keeps the state of the application. Yeah. And so you have one of them in every cluster, but then also you have, so this API, the master exists in every cluster, and the federation control plane sits on top of that.
What does the worldwide geolocation load balancing?
We'll get to that. Cool. So now, if we're going to deploy a service is another thing we can federate. We saw before they're a way of addressing objects that run in a cluster. So now we want to deploy it across our federation. So we want to target all of the things that have this label, Nginx, and then we want to make them available on port 80 and use a type load balancer. So what this will do is it will create a load balancer in each cluster, in each shard of the service, and it will connect those services up so that we have an IP address endpoint for each. So you get a DNS entry that references that load balancer and that service name in each cluster. You'll also, so for example, the US East cluster, the service that's load balancer, its IP address is here. I'd like to be able to use this one if I remember. But all 4 of them together, we have this entry here where it publishes all 4 A records. And what that means is you can do round robin load balancing between those things. And you'll see that in the example. Now this is also available inside the cluster. So you're able to address your service. So if you have, this very simple example only has one thing in it, but if you have a second service in here that wants to talk like a front end to a back end, by default it will look inside its own cluster on a local IP address. But if it can't talk to that, then it can call out to a different cluster. So if the service isn't running in your Japan shard, then you fall back over to your US shard. Now we can start doing cross-cluster service discovery. So this is a slightly different example here where we say we have an on-premise cluster with an F5 load balancer. So a customer might say, by default we're running our own data centers, but for recovery purposes we also operate here in US and in Europe on Google. So if you look up that service, so we're going to look up the Europe thing there, you make your call to DNS. It says, all right, well it returns the addresses for clusters 3 and 4. And then it's up to you as the user and your client application to run Rob. Now let's say that there's a problem, there's a data center outage in our on-premise data center and that goes away. So that's going to disappear. Now remember we define our state, we say we want there to be 4 replicas of this. And right now there's only 2. So the federation control plane is going to realize I haven't got what I want there to be 4, I've only got 2. And so it'll find a place where it can run 2 more. And for a Europe service, it has to run in Europe, it'll turn 2 more on. So we scale the Google data center from 2 up to 4. And now our user, having failed to connect to the on-premise data center, gets routed to the Google. Now on Google Cloud Platform, we can have load balancers that work across regions. So most load balancers, so TCP load balancers in Google and everything else in the rest of the industry are regional. So you can balance between things that are in the US, or you can balance between things that are in Europe, but you can't have one single IP address that sits on top of both of those. You can with our global load balancer, so you can actually put an ingress object in front of this. And what that means is that depending on where your user is, they can be routed to the part of the service that's nearest to them. So we have a Chicago user might access the American cluster, and a London user might access the Europe cluster. Let's break out here and have a look at the demo. All right. I have some clusters running here. So using Container Engine, I've deployed 3 clusters. One's running in our Asia East zone, one in Europe West, and one in US Central 1C. Now, in one of those clusters, in the US Central one, I have deployed the federation pieces as well. Yes, no, I have a machine set up with a whole bunch of convenient aliases. Because I've got 4 different clusters to connect to. It's way easier just to type US than to try and remember the name of those things. All right, so US again. So we create a namespace in that cluster, and we have the Federation API manager and such. Now there are a few things that Federation supports right now. It's secrets and configs, services, not the deployments behind the service at the moment, the replications, but that'll be in one of the upcoming releases. But we can say, for example, Federation get services, and you can see the services that are running here. We have an application that we use this demo made up of 4 different pieces. And then if we look at the various clusters underneath that, you'll see that so the external IPs here, it lists more than one of them, but you see it matches that first one there. And these services exist in all of the clusters that we have running in. So this Kubernetes service you see here, it's a system thing that's it's not part of the federation, it's deployed only to each local cluster, but those things, the only other things I have running in here are the things I have federated. Now, if I go back to screen, so we have a little dashboard here, which we're going to use in a moment to look at traffic to our cluster. But the thing we're actually going to demo, we have have a little API service that we're building. And let's have a look at what we have here. So it's written in Go. I am not a common I'm not a regular programmer, but I will be able to talk through most of what we have here. Basically, what our API service does is it gives you a random message out of 4 messages that we have here. So in this particular case, you see the 4 things it's going to return. What we've also done is we've used a thing called Prometheus, which is a monitoring toolkit. It's very easy to add to applications to publish time series data. So for example, what we have here is a counter of requests that are being made to each verb and response code, and then we can send that out to a service which will graph that for us automatically. Or in this case, we're going to actually just have an endpoint which we display. And aside from all that stuff, it uses a pretty standard HTTP service to basically just have one endpoint that's API/next. And if we can build that, it's nice and fast because I've done it before. And so now using Docker to build that, I think you may have seen the Docker file earlier. But right now, running on my local machine, I've got this application which is listening here. It's every second it just outputs. It's the statistics from the Prometheus client I was talking about before. So if I go to that endpoint, I get one of those responses. And if I refresh, I go through, and even better, going through here, I see that there's some statistics. So our endpoint's being called, it's getting a success to each of those things going through, and then after that you can see for each request, then there's a summation line that basically says so what number of requests per second that we have. So that's our very exciting backend application. And we have published this to a Docker repository, which we will use to build an application out of. So that service, that backend service you saw before, so that's not right, thank you. Okay, so we have on this particular machine the internal balancing IP we talked about before is there, and we also have a load balancer that's publishing that endpoint. And so if I were to go to that, like I did on my desktop, I can see a hosted version. I mentioned before that we publish all that in DNS. So these services, so the backend service we're talking about here, Open Masher backend, you'll see that this one here, that's that same IP address. So these things, we have one instance, one load balancer running in that cluster, and that publishes that nice to be in DNS. Now what we have, this little traffic aggregator here, you see that traffic that I faked before, is actually being served by this cluster. So we have a nice little front-end application running here in the cluster as well. And so if I click that, there we go. Every time you click it, it makes the call to that API, and you see the response that it serves you there. And again, if I go back to my stats page, you can see in this case, the traffic is being generated.
Why does it say V1 and in the cutscene it say V2?
It says V1 because move that out there to see it. So this is version 1 of my application. It's just arbitrary, I've decided that. So we had a few things there. Then you can see that traffic come through. So if you actually want to get your phones out now and go to that address, or scan that QR code, let's see if we can generate a little bit more of the refresh ones.
Why are we not routed to Europe?
Why is it not routed to Europe is,
Israel is faster to the US, we have a direct line to the US.
I would love for that to be the actual reason.
Really?
The reason in part is because I didn't have time to get the federated English stuff we talked about and set up. And so this is actually just using DNS, and your phone is probably taking whatever the first entry is in there. So actually some of you can see there, some are going to Asia, some are going to US. You guys aren't pushing the button hard enough.
Did you put the S on the site?
No, that's the QR program that you use on your
Oh.
iPhone. I have that exact same problem. It's just www.cube.pw. Okay, so you can see here the same application is being served. It's very simple, but you can imagine it could have replication for databases and things in the back end. But this is now our little application that we wrote there, pushed up to Docker, being served in 3 different workload clusters. Now, in saying that, you guys weren't really clicking the button as hard as I would like. So what we can do is
Simulate something.
let's make some load. Now, in this case, again, we're using the sending the same command line we sending to our federation. We're saying this replica set that's running here, running our load tester. There's currently no replicas running, but we said we'd rather there were 3. And now we have 3 replicas sending about 1,000 requests a second to their own cluster. But you should be able to see that, well, you can still hit the button. And now we can make this number substantially more than 1,000, but for the purposes of this thing. Now the question Shay asked before was why did it say v1? Well, actually, if you remember the code from before, there were 2 sets of things there. So we have simulated, this is what version 1 of our app does, and it just hit this and various things. But at some point we're going to want to upgrade, we're going to want to change this, but we actually have people accessing this running in real time. So we have a concept called a rolling update in Kubernetes, where if you have multiple replicas of something, say you have 10 of them running, what we really want is to get from 10 of version 1, or 12 in this case, to 12 of version 2. We take one off, we start a new one, we still have 12. We say, let's go, we take another one off, we start another new one, and we repeat that until we get to the end. And we can do this while the cluster's under load. So I go back to my terminal here. Remember what the instruction is. It's rolling update.
Why are you not using deployment?
Deployment, we are using a deployment. The deployment object that handles this isn't federated yet. So what we've done for the demo is we have the deployment created in each of the 3 clusters, but we just address them one at a time rather than as we're building federation out, we're putting more things in. So this takes 3 commands right now, but it will take 1 once we've got it. So this command here, again, it does the same thing as my little US command line does. It applies version 2 to that, and so you'll see there that of my things here, it's rolled very quick for the demo, but you'd normally space that out over time. We have now only 8 running version 1 and 4 running version 2. And if I were to do the same for my other 2 clusters,
Yeah.
and so now, as you go through, now during the process of that, if you was hitting the button as I was doing the update, you see some of the blue ones come through, and now the responses you're getting are from version 2 of our API, which we've rolled out. And it's very easy to roll back to that as well. And all that was done while the cluster's running and running out the load. So this afternoon was spent trying to make the magic ingress work, but unfortunately. That's not really good for you. All right, so what you saw there was a stateless application. There was no concept of state. Each request just returned something at random. There was no communication between the nodes. There was no communication between the clusters. Those are the kind of apps that quite often deployed for front ends, but not for back ends and middleware and that kind of thing. And you've probably all heard of 12-factor applications. We talk about things should be stateless, get their context from the environment, all these kind of things. But when you start wanting to do real work and run your database, you say, well, that's not good enough. So, to support running stateful applications, instead of this deployment in its replicas, we've now moved to a concept which it's just been renamed stateful set in the last week or so, but the code name for it was pet set over time. And it goes to the analogy that some people use to say that pets are things you name and you care about, and cattle are things that you eat. And you just have a number of them in a field and don't really care about them. My uncle used to keep 2 cows. One was called Christmas and one was called Easter. But as opposed to our replicas, and like if we, the pods that we see, the pods that we see before, they just get a random token at the end for their name. But what we want with a pet is we want it to have a stable host name that we can guarantee, and we want them to have an order. So instead of just having a random token at the end, you say this is pet number 0 or pet number 1. And that way we can say the first one is more important, and it is used for database systems that need to do some bootstrapping or need to prepare what they operate. And then we can also allocate storage to that so that this database service always has this disk attached to it. It has the volume, and no matter where this pod gets put, it's not like the pod's going to be here and the disk is somewhere else, so you don't have to worry about replicating that so much. So this is the replica set case. You say I want 3 versions of my replica, and this again, the web server, it just gets a little token at the end to keep them unique. And then if you want to scale that up, you might have an autoscaler. It says, right, there's lots of people hitting this, so I'm going to move up to 6 replicas. And there we go, we move up to 6. And then later on, if it says, all right, I'm going to scale down to 2, it doesn't really matter which 2 that it keeps. It might do it based on scheduling decisions or just the alphabetizing of the order of things or anything, but there's no ordinality here. So it just might keep those 2. But it does what you want and says, I should have 2. So with the stateful set, you have 3 with storage, and this happens. So the first thing, they don't all get created at once, they come up in order. So we have a pod, in this case it might be for a database, so we'll call it db-0, and it has a mapping to a disk. And the reason that those things are 2 different things is because the way Kubernetes works is that because we've got infrastructure underneath the line and things above the line in 2 different teams, you say I want this much disk, and then the system decides how to claim it from the pool underneath, but they're effectively the same thing. So we have a container with some persistent storage, and then once that's up, it'll bring up a second one, and then I'll bring up a third one. And on this, you could imagine MongoDB or Cassandra or anything that wants to have some idea of system that it can discover its peers and do communication between them, or it can say this is the first one that came up and I can do some sort of cluster startup and send things out to the other ones. If I ever want, sorry.
A question specifically about the volumes that you actually attach. Do you like specify this is a part of some kind of physical disk, or you just ask the pod to have some persistent disk and it allocates specifically the amount needed, let's say like 10 gigabytes or 100 gigabytes, and then it like auto provisions things and attaches it and then like keeps it or whatever?
Yeah, the answer to the question depends what type of disk you're using, and that's by design, because on top of the line you should say I want some storage, and you might specify a size. Like right now you basically say I want 100 gigabytes of persistent storage. If you're on cloud and you have a disk that you can attach to it, then we can automatically provision that. We can say create a volume of 100 gigabytes and attach that, and then that's available later on. If you're on premise, yeah?
Yeah, a question about state and auto-scaling. I wonder if Kubernetes in general very much constrains architecture to a very specific architecture. I have a 100 gigabyte Java virtual machine, a huge heap which is necessary for fast graph traversal algorithms. That's very unusual. It takes half an hour just to start up reading all its graph from the database. It's unusual, but it's not unheard of, and there's good reasons to do it this way. And I've also been told that Kubernetes would slow down the memory access and the very slow garbage collections. So my question related to this is, would this support that very unusual architecture?
Yes, but it's not really related to this. I think we'll need to finish both things off separately, but the concept of running inside a container is basically saying, here's my process, and then put some of those restrictions. So make sure it can't use more. You might, if it's 100 gigs in your case, you might want to say it's allowed all the RAM on the machine, or you might want to say it can take up an entire machine. But at that point, basically running inside Docker, it's a process that runs on a machine, and as long as nothing disrupts it and your machine doesn't die, it will continue to run on that machine for a long time. So there's no reason it shouldn't do that. If, in the case of, like, one of the things people use this for is to work around cloud environments or hardware failure or whatever, so if the service goes down because I have a power cut, then turn on somewhere else. So if you need to reload a big index from disk, then this particular thing here will make sure that it brings up, and it's not an empty index, it doesn't have to regenerate everything, it will have everything in the state that it was before it came down. So in the case that you have to restart something for whatever reason, this attaches those two things together conceptually. Just to finish off on the different types of storage, the claim here is basically you could have iSCSI or NFS or something underneath this, and it's up to the people down here to decide how to give you storage. If you're in a data center, it might be they physically have to come and plug in their disk, because in the cloud you can just call an API.
Yeah, mostly I was talking about GCP, and
Yep.
when I want to attach a volume, I'm thinking about, okay, I provision a Kubernetes cluster.
Yep.
I haven't attached any disks to it. And then I just, like,
Yes.
with the provisioning of the actual deployment, I'm asking for a specific disk in
Yeah.
a specific
So,
size.
On clouds, by default, there is an automatic provisioner, which says, you asked for that, I'll go get one for you and give it to you. And you might, like the reason that this is shown as a relationship is that this thing is fulfilled by this disk, and so it's got an ID, and we make sure we reattach it later. So you can, that lets you say, I want to start a pod with this exact disk that I had before, if you've done that. But the first time you create that, it will just give you that by default. You can turn that off, and you can set
Awesome.
only certain people are allowed to do
And
that.
the thing is, the question comes from when I provision a new node.
Yep.
Not even Kubernetes, a regular machine in the Google, and then I attach a disk.
Yes.
I just ask for it for a disk.
Yep.
I need to format it and then to mount it.
Yes.
Do I need to do the same thing each time when I do provisioning of disks in Kubernetes and
So
Docker?
GCE instances have a script which, when you attach the disk, it automatically makes sure it's formatted and mounted. So a
Okay.
convenience thing to say, if the thing you attached isn't set up for you, set it up for you. So that's only for things that have not been initialized before. Cool. But the assumption is that it will have whatever the thing underneath provides, and what we provide with PD is ext4, and presumably similar to everyone else, but POSIX-like stuff.
In 1.4 you also can specify the storage class.
Mhm.
So when they move to the beta features, that's one of the additions. So you can define if you want SSD or
Yeah.
Yeah.
disk, and you can choose that.
Yeah, so the two classes, well, the three classes of storage, we have network disk, which is either hard drive or SSD, and locally attached SSD. But the storage class could be on my fast SAN or on my slow hard drives in my data center, just as much. So.
First of all, when will this work in the container engine? Because it doesn't now.
I'll tell you in 2 slides time.
It's okay. And the second thing, the attachment of the storage. When a system goes down, when a pod gets relocated to another one,
Yep.
it needs to disconnect the storage from the machine, move it to the different machine, connect it there,
Yes.
and
That's pretty magic that's possible. Like, you
Magic.
can imagine the old days, it's like unplug something and walk somewhere. So.
that's really nice if it works.
Yes.
It
Does it not
doesn't
work?
always work.
I tell you what, it works more often than it does on certain
That's-
other people's clouds that we don't like to talk
That
about.
is true.
So it is.
It works
yeah.
better than AWS, but still, it
Yeah.
does get hang.
Yeah, so it is, I mean, that's a question for our cluster management team, because you need to be sure that it is physically detached from the first thing before it's safely allowed to be attached to the next thing, and in the case that this thing just crashed, then it takes a while for it to catch up and be satisfied with that. So. If we didn't have enough light here already. All right. Carry on through this. Now in the case here where we want to scale down, we say we only want 2 nodes. Later on, if we were ever to scale back up again, we might want to reattach to that volume because it has important data, and so instead of replicating, we don't want to, instead of having to rebuild everything by asking its replicas, then we just can get the delta from it.
When you scale down, how do you preserve state? Is it something long to running, like a transaction? How do you know, how do you wait for commit or?
So there's the application logic question. So you can instruct your thing to only drain a node when all the connections to it are finished. So you can say, I'm happy with that. But the scaling down, like in the 12-factor case, it's kind of designed around the idea that things can come and go. Obviously, we hope they don't come and go quite that quickly. But cool. So just a few more slides here to finish up. Lots of people are interested in the committee. We have KubeCon, who's just finished in Seattle the last couple of days. There's been a whole bunch of really cool talks there. Microsoft announced a hosted Kubernetes service. So ours is a fully managed service, and they're just starting off with sort of automatic deployment, but they've also open sourced it, so showing a lot of interest there. So 2 out of 3 public clouds now have service. And a lot of behind the firewall work as well, so vendors who are working with us to make it possible to run this. Here are some of the companies who are contributing. There's over 5,000 commits in 1.4 from 25% more contributors than previously. People from operating system vendors, virtualization companies, people selling grid computing, everyone. It's really taken off a lot more than we would have hoped. It's number 1 or 2 by on GitHub metrics for people sort of enthusiasm. It's a very calculated way that they figure that out. But it's also the base for a lot of other external projects, hosted versions and various other things. So we've recently working on tooling for automatically deploying things inside clusters, a thing called Helm. So you can take a description which says, here is how I want to deploy a WordPress, and just throw that at a cluster and it will give you the bits underneath required to make that. 4OS just announced things called operators, which are custom controllers, so that if your particular application has some sort of way of setting itself up, so etcd, for example, when a node joins, it wants to send things out to all the other nodes, so it uses, for example, the stateful set to do all its management, but then it also has some instructions that basically say, given that I need to run these commands when I've joined a cluster in various orders. So a lot of add-on work. The base is really there, and people can happily make it easier to run applications. Here are a few of those applications: the cloud providers, continuous deployment vendors, monitoring tools we mentioned Prometheus before, storage, and so on. Here are a few of the customers. So we're seeing great adoption in media companies. Whether or not I should go back to mentioning this, but the USA Today election tracker, people who are watching state-by-state results for anything, for any reason, the last couple of days, that was running on Kubernetes.
The most exciting one is Pokemon Go.
Yeah, Pokemon Go. Do people still play that here? Anyway, it's nice to know that if they hadn't changed the dynamics of the game, that it would still be able to scale.
When we were in London, we actually talked to the guy that was there, and he told us that soon enough there's going to be something new and amazing that will get people excited about Pokemon again.
Change the
once
color of the
again.
button, and they're going to change the random messages.
Yeah, that's exactly what I told him.
If anyone's familiar with psychology, a thing called a Skinner box. It's basically you click it and random things happen, and eventually the pigeon might get some food or anything like that. It's basically you click the button and sometimes it says woohoo. I believe Pokemon Go is basically just that. Yeah, so at KubeCon this week, Sam from Box.com, they're a big adopter of Kubernetes, he gave a talk about how to pick a cloud these days, how to pick a private cloud. And this is from before that, but he's saying that it's the platform that they've adopted and they're really looking forward to building on. Journalists are behind it. This was an interesting article from Meta, but basically he said that it's the experience that Google brings to this, and both from a technical point of view and the community that we're building around it. Here are a few things that are coming in the next version. So we are taking a lot of features that are currently in alpha. Alpha features you can't use on Container Engine today. So Container Engines for production, if we let you run the alpha stuff, it might break all the time. We don't really want to allow that. So things that are in beta or above work on Container Engine. The stateful set stuff I talked about before, that's in alpha. So it will be beta in 1.5, which will come out on or about the 8th of December, and you'll be able to run it on GK. The reason it didn't go beta before was basically we just didn't have enough people building recipes for it. So how quickly it progresses through really depends on how many people use it in the community, whether we think it's the right idea to take forward. So more things like we mentioned deployments before, we create them per cluster at the moment, but they'll be federated in 1.5. We have more metrics-based scheduling. I think we do anti-affinity and affinity in 1.4. Maybe notability is coming in 1.5. And the easy setup that we've done for a single cluster in 1.4, we're moving out to set up both highly available masters and to easily set up a federation. So Kubernetes is open, it's open source, it's open to ideas from everybody. We have a great Slack channel. We have, I think, now over 8,000 people who are on Slack channel. Code's out there. You can raise issues if it turns out that your federated ingress doesn't create a bug, and the guys who are maintaining it will very quickly debug it for you. It's very easy to get started. We mentioned Minikube before. You can just download that and run that on your laptop, and then that gives you a VM running a single node cluster which you can test everything against. And then you can go hit the button on Google Container Engine to set up clusters. Very easy. I didn't even have to do anything with Quota to get those 3 clusters running in my account. $300 free trial for anyone who hasn't set up on that already. Hopefully you guys all are. And that's me. So I'll take some questions, but thank you very much. Yes.
Great talk.
Thank you.
So 2 questions. First of all, nowadays when we manage our cluster with regards to scaling up and down, you mentioned you could specify like in the replica control number of replicas. And then for instance, you state like I want 10 of these.
Yeah.
And then if for some reason I have higher load, then I would maybe increase it to 20 or something. Is there any planning to support something like auto scaling, like dynamic auto scaling?
Yes, it's there.
So
Both of those. So there's 2 types of autoscaler. There's so you have a certain number of nodes in your cluster, and inside that you want to say this single pod. So how you should size to your question before, you size your pod based on this is the right combination of memory and CPU for this particular workload. My API servers, maybe it can serve 1,000 requests per second or whatever. And so what we do is we have a thing called a horizontal pod autoscaler, and you set it up listening to some of those metrics, to maybe some of those Prometheus metrics, and say, well, I've got incoming traffic of 1,200 requests per second. 1 pod's not enough, turn on 2. Now I think I can do this. And so you keep going up, and you can set that on CPU usage of the pods, or you can set it on requests per second or something, and that will scale up to the limits of your cluster. So again, behind this in the real world, clusters to us are things that live in a building and are made of real servers, so they have a sort of finite size. When you're on the cloud, the other thing you can do is say, well, hang on, I just make my cluster bigger. Turns out lots more people want to play Pokemon than I thought, I'll just grow the cluster. And so you can also have a cluster autoscaler, which says, I've run out of space to run work, and the number of machines that I have, turn on more machines.
Cool, great.
Both of those things are there.
Great. Maybe second question. So, if I want to, is there any planning to introduce something like a smart gradual release mechanism? So today I can probably, deploy to all of the cluster, and maybe I can specify deploying to only like a certain number.
Yep.
But would you consider adding something like, a mechanism that checks some KPIs in order to decide if indeed it is advisable to continue with the release?
Yes, so the deployment object sort of encapsulates what you want. So your deployment will include a certain number of replicas, but then it also is the thing that you issue the command to say update this deployment from version 1 of my API to version 2 or something like that. So you can extend that, but you can also say, all right, well, I'm going to have 10 replicas of version 1, and then I'm also going to have a second deployment, which is version 2, and I'm going to set 1 replica up with that. And then with the labels on the service, you say address the front end, and it will catch everything. So you don't say, if you said front end version 1, it would only catch the 10, or front end version 2, it would only address the 1. But you just set your service up to say front end, it will catch all of that. And let's say you've got 9 of these and 1 of that, then 1/10 of your requests are going to version 2. So you can see how it behaves under 1/10 load. And then you can switch over to 20% or something.
This is via labeling?
Yes, so this is without anything else, just with labels. You can do a canary deployment. We say I'm going to deploy a small number of these ahead. You can do the stage rollout. You just basically increase it. So that's all a rolling update does, but you can control that yourself, or you can just issue your own commands to say over time go from 1 to whatever. So we do rollouts internally. We roll out to a set of people who have opted in, or a set of clusters that we use for testing. If it works there and nothing horrible blows up, then we'll say blow it up to 10% of the users, so then 20, 40, so on. So if, for example, you go to the Play Store and you can't download the app on day 1, that's the thing. It's because a small group of people get it first to make sure everything works, and then over time it rolls out. Cool. you the question.
What's the boundary between where you should choose Google App Engine or another platform as a service in contrast to Kubernetes? After all, Google App Engine does auto-scale and so on. Of course, I could partially answer the question. I could say if you have an unusual setup that doesn't match exactly what App Engine provides, but maybe you could answer this.
Yes, so App Engine is our platform as a service. It's built on top of our underlying container stack. It has a bunch of assumptions and things based on the time, and we are rebuilding it to be on top of VMs for people who need more flexibility. So there's two versions, the standard version and then the flexible version. It uses very similar technology underneath, but the flexible version basically says your entire thing runs on a single machine. And because we don't, the way the deployment of things work. And then it is a bit more like, we don't call Kubernetes a platform as a service. And we say it's a thing that you could build on top of. So there's a thing called Deis, for example, which is an implementation of something like Heroku, where you say git push something, and then our thing consumes that, and it just runs inside your cluster and makes your Kubernetes cluster more like a PaaS. But PaaSes have, again, App Engine very similar. It has runtimes and things that make sense. So you can use this as a basis for something like that. We like to think of it as being sort of a continuum. If you just want to give us code and don't care anything about how it runs, App Engine's fantastic for that. On this end, if you want to care about what operating system you run, and you want to care about kernel versions and stuff, you can run a virtual machine. Container Engine's very much in the middle of those two things, so you want some control, you specify the entire application, but you don't get to decide what version of Linux it runs on. You don't get to decide kernel stuff and everything. So stricter boundary, but you can then pack more work together, and you instruct it a bit more. You say, this is some more information about how my things relate to each other, and you get the benefit of packing it in together. But ultimately, we want you to be able to run like the same load balancer that's doing that ingress. You can say, this path is served by App Engine, and this path is served by GKE. So you can segment off by path, and we want you to say, the part of your application that makes sense run on App Engine, the part that makes sense run on GKE.
There's some concern about the, well, it's kind of a GCE question.
Take it.
The container
I
engine
can.
ingress
Yeah.
controller is actually a level 7
Yes.
ingress controller. There's some issues about its performance, so there's a lot of tools.
How?
That's from the documentation. From what I've tried, it didn't work. So
Yes.
I don't
Okay.
know
So
what to say.
it is a complicated thing because it's made up. The way that we describe how the load balancer works, instead of just saying connect this to that and then having lots of configurable knobs, we've broken it down into 5 different components. And I probably can't remember them all off the top of my head, but this again is an example that we built a global load balancer, and we figured out, well, the things that you think don't quite work, and you need to separate this from that, and you need to do these things, but you don't know until you've done it. So these things are separate for a reason, like health checks and backends, you attach a health check to this or whatever. But ultimately, all you should do from the Kubernetes perspective is you mark your ingress and says, talks to this service, and then it will create all those things for you. And it works within a single cluster. It almost works in the federation. It didn't in my example today, so I didn't show you. But the pieces are all there so that you can change them if you need to, but it's sort of a complexity you don't think about if you're not touching it.
And I have a question about environments. Once I want to run both the testing, staging, and production environment, are there any best practices to running it over Kubernetes? Let's say a Kubernetes cluster separated for development and staging and everything, and
Yep.
production, or just labeling?
Next is.
Yeah. It's a trust question. So the 3 primary options, so you can have completely separate projects on Google Cloud.
Okay, this is a real big separation.
Yep, that's nothing I could possibly do. And then you can have a single cluster where everybody runs inside that. Namespaces make it easy to keep people separate from one another inside there and to make sure that you don't have conflicts. But because containers are processes that land on a machine and we hope are secure, but then they have a copy on write vulnerability in the kernel, and you might be able to find a way as user A to read user B's stuff if you're on the same machine. If you can cope with that, you can pack work, like the more people's work you can put on this cluster of machines, the better you get the benefits. So that's why we pack batch work and real-time stuff together on the same machines, because we did a analysis of this. It would take 25% more machines if we separated them out, our MapReduce workloads and our serving stuff. But that means that you would have to pay for, if you have 4 data centers, you have to build a fifth one, basically. So you get benefits of that depending on what you can accept as risk.
And are there any best practices to planning these kind of deployments, like architecture-wise? Because when I want to come and, like, I don't know, start using Kubernetes, okay, a good place to start from would be guidelines. I don't know. Are there any resources to build these kind of guidelines?
They're being built out, and we have a lot of people. Anyone who work in a consulting company or anything, like we find there's a lot of consultants who are starting together to bring these things. We're trying to standardize a few stuff. So the workshops that people run, for example, we're trying to get these practices from the community and find a way to codify them. So we're quite confident now that the tools are good. So we knew the patterns were good. We now know that the tools are good. Now it's really, here's a chart that says here's the best way in like YAML format to deploy a 3-tier web application or something. And so that's the way we want to start codifying. So it's on its
And
way.
maybe how to implement the CI and CD over Kubernetes.
Yeah, so I was mentioning to guys I was talking to earlier today that we had a thread internally last week where someone said, how should I deploy CI to containers? And we had 5 different people respond with 5 different perfect answers that were completely different from one another. So you can pick whatever tool you want, but it's one of those, like there are 3 or 4 different ways. And we haven't traditionally, as a vendor, like to say, like, you can pick whatever network overlay you want. We don't want to say this one's the best because then it stops people wanting to run it. So we want it to work everywhere with everything.
No, exactly. I do believe that too. But are there any like pointers to this? These are the 5 options, or it's just hearsay by people with the team.
If you asked me what would I improve first, I would say our documentation, and I think that this is a part of it. I think that it's coders don't like to write stuff well, and so that's why people like me have a job. So we'll work. Yes, sir.
So I think there will talk at KubeCon about managing unikernels with Kubernetes. So I think it's possible to manage VMs rather than containers with Kubernetes. And where is it? Can you elaborate about it? And where it's on the roadmap?
I don't know. What I do know is that Hyper.sh was there's a Chinese company originally who built out a container runtime where every container runs as a lightweight VM on top of a hypervisor. And so that makes it much safer because we generally trust hypervisors, but we don't trust the kernel. And so they are working on a Hyperneted system, which, given a pool of machines,
Yeah, but
runs.
they don't use Kubernetes, right?
They don't. Like they have a hosting cloud thing. I don't know what that runs.
I'm familiar with Hyper.
Okay, but they're working on a thing called Hypernates, which is a version that combines those 2 things. Everyone loves the names. So Federation was called Kubernetes for the longest time. But yeah, I haven't seen that talk. So.
And for question, you said that alpha features will not work at the JKE, but there's some alpha features that are enabled, like scheduled jobs or bad jobs.
Jobs are beta, but scheduled jobs
Like
are
cron.
alpha. Yeah. So scheduled jobs were in alpha this release, and they should be beta next one, I think. So a problem is that I say we block this. We accidentally didn't block it for a while, so people were able to run stuff that they shouldn't have. And then there's other things like this is only within the master. So our master disables you from running things, but like all the federation pieces, they just run in container space, and some of them are alpha, but you can run those because they're just containers that run.
You can have an alpha cluster for this thing.
Yes,
but
that's a good
get
point.
deleted after a month. Or
Yeah,
so.
we have a thing where you can just turn a cluster on and say I'm going to test it. It will run with all the alpha features, but hopefully, I'm sure we'll have new things, but most of the things that are in alpha right now, big beta and 1.5. Cool. One more?
A little question.
Sure.
Is it possible right now in Kubernetes 1.4 to separate network access between namespaces? I tried Kubernetes like 6 months or 4 months ago, and I didn't find a way to separate network access between nodes and pods between namespaces. Is it possible?
Yeah, there's a thing called Calico, which I recommend for that. It's a
Someone else also said to try. Is it native, more or less native to Kubernetes, or completely external tool that I need to bake in somehow into the cluster?
It is both. So by design, Kubernetes is all about interfaces and it's not about things being built in, but Calico implements the plugin interface for the CNI, container name networking interface. And it lets you do network policy. So it lets you define things and say these things can and can't talk to that. We're building network policy stuff into Kubernetes, but it does work today. That's why we're using that for the USA Today thing I talked about. So have a look at that. There's some good demos, videos where they show exactly that. We are waiting, I think, till the network policy object, so the stuff that they've done outside of Kubernetes, we're bringing some of that in to say, here's an object that defines a network policy, and then Calico will just consume that. Eventually, so I mean, that's probably 2 releases away from being in mainline. You can use it today, but you can't use Calico on top of GKE until we've done that. So you can run your own cluster using their network plugin.
Okay, and it's okay for production? What
Yep. Yeah,
okay.
we're seeing big names using it. And,
Okay.
yeah.
Right,
Yeah,
thanks.
so we have Calico and Weave and Flannel and these things. They're also the plugins that let you do software-defined networking between the nodes in the cluster. Google Cloud has its own SDN stuff built in, so you don't generally need it. You can run them on top if you want to.
Canal ever?
Canal is like a brand name that's Calico and Flannel together, and I think it's still happening, but they announced a new version of Calico and the KubeCon is on it. I haven't put on all the details. But. Awesome. Thank you all very much. Stay around for about a couple minutes.